is to introduce single field inflation and basically go through the calculation of how to work out its perturbations. Actually, that's also, I'm going to be brief and sketchy at points, because the point of the final homework is to walk you through the calculation really in detail and have you check everything so you feel like you haven't just had a magic wand waved in front of your eyes. But yeah, so that's the idea. I've basically given up. I did on getting to a discussion of initial conditions in the wave function of the universe, unfortunately. Maybe at the end of the class I'll just point you to, if you want to read about that, where to look. But anyway, okay, so inflation. So the idea, in earlier lectures we had discussed the motivations from the homogeneous standpoint of trying to tack on an epoch of the early universe prior to radiation domination, when A double dot was greater than 0. So we want to tack on to our picture of the universe an earlier epoch where the energy density was approximately constant, varying sufficiently slowly that when you plug this into the Einstein equations, the solution for A actually has A double dot greater than 0. So this period, this hypothetical period back here, is the epoch of inflation. And this moment where it ends, and whatever energy density this is, decays and converts itself into particles of radiation, maybe standard model particles. That epoch is going to be called the moment of reheating, which is kind of a misnomer. That has a historical origin where it was assumed that there was a hot period before this, and then this exponential expansion exponentially cools the universe, and then you want to heat it up again. But really, we have there's not even the remotest reason to believe that there was a prior epoch where the universe was hot, either theoretical or observational. So anyway, but it's still called reheating. Okay, so, and again, the idea now is to say that there were these homogeneous motivations back in 1980, the flatness problem, the horizon problem, the monopole problem, that led people to think this was a good idea. And then within a couple of years, people realized that the simplest model that could do that is just a single scalar field, is the so-called idea of slow roll inflation, where you have a single scalar field, and it's initially displaced. If you plot its potential, so you plot phi, the displacement from the origin on this axis, and the potential on this axis. Okay, it has some origin. The bottom of the potential is roughly at potential energy equals 0, and then the potential does something up here. But the bottom line is that if you displace the field enough from the origin initially, if somehow in the early universe, by some unknown mechanism, the field is initially not at the origin, not at the minimum in the vacuum, but up here, and okay, so and it can monotonically roll down, monotonically evolve down according to its equations of motion. Then if out here the so-called slow roll conditions are satisfied, so sufficiently far from the origin, the slow roll conditions are satisfied. In other words, the slow roll parameters that you met, I think, in the tutorial, right? You meet the slow roll parameters epsilon and eta in the tutorial? Yes. Who's with me on that? Yeah. So, these are just quantities you can evaluate as from the if you know the functional form of the potential at any point on the potential. So if both of these guys, you want both of these guys to be small, far away from the origin, or let's say you want the absolute value of this, you want the absolute value of eta really to be small. And then as you get close to the origin, if these conditions then fail, you get to a region where these guys become comparable to or bigger than 1, then that turns out to naturally lead, the homogeneous evolution naturally has the property that that when you're up here in the quote-unquote slow roll regime where these guys are satisfied, if this is really the energy density that's dominating the universe, then A double dot really does accelerate. A really does accelerate, whereas once you get down here and the slow roll parameters fail, the field just begins to oscillate like an underdamped oscillator around the bottom of its potential, and the field and the universe really does transition to decelerated expansion. And then the idea is that if this guy has some coupling to some other particle, so it's not a stable field, it doesn't just sit here oscillating forever, but gradually it's basically like a gas of massive particles here, a condensate of massive particles. If those massive particles can then decay into other particles, which ultimately decay into standard model particles, or maybe it can just directly decay into standard model particles, then that's how this reheating happens. So it transitions to a decelerating regime and then turns itself into radiation when it decays. Okay, and so we said, so that explicitly the action for the model that is just this guy. So it's just the ordinary Einstein-Hilbert action for gravity, for general relativity, and then we just add to it the Lagrangian of this scalar field. And again, so we just derived the classical equations of motion from this. So we have some equation of motion for phi. And we have some equation of motion. That's what we get by varying phi. By varying g, we get the Einstein equations. Where T mu nu is nothing but the T mu nu of a scalar field, the stress energy contributed by this scalar field. And so then the first thing, again, we do is we look at the homogeneous solutions of this equations of motion. So if we take the metric to be the FRW metric, so G mu nu is the FRW metric, which in some sense only depends on time, doesn't depend on spatial coordinates. And phi we take to be a homogeneous scalar field that doesn't depend on time, is a constant across each slice, but is just varying in time. We specialize these equations of motion to that case, then the classical equation of motion for phi reduces. Let's call these homogeneous guys. Let's use a little subscript or superscript 0 to denote the homogeneous guys. So the homogeneous limit of this equation is like that, and the homogeneous limit of this equation, is the Friedmann equation we've already met. And in a moment, okay, so in a moment, so as we said, the initial acceleration of the universe, you may remember, one of the original motivations for the initial acceleration of the universe was that it drives this term to become negligible relative to this guy. After a lot of accelerating expansion, this term gets suppressed relative to this guy. So let's imagine that's already happened. And then rho, again, the homogeneous energy density of a scalar field is rho is equal to 1/2 phi dot squared plus v of phi.
Nathan?
Yeah.
Why do we expect to still have the Einstein-Hilbert action at energies above the Planck scale?
Yeah, this is related to the thing you were asking about the other day. The energy is actually way below the Planck scale.
But the phi is that is above the Planck scale. We want these things to be small.
Its displacement from the origin is above the Planck scale.
Yeah.
But the energy
okay.
density, the curvature that it induces in space-time, is the curvature scale is much longer than the Planck length. The energy density is way below the Planck scale. It's because it's, in other words, it turns out to be an observational. Okay, so let me just say a word about that. So it turns out to be an observational fact. So what we were discussing the other day, and in the tutorial, is that I drew a disgusting potential here, just because I was sort of trying to be not imagine that I knew too much about the potential, because we don't know really what the potential is in much detail. But I was making the point that even the simplest potential does the job. So even if you just take V to be a simple quadratic, an ordinary mass term for the field phi, that does the job. Now when you fit, but then as you found in the tutorial, to get into the slow roll regime for this potential, you have to take phi to be bigger than the Planck mass. But that does not mean that the potential or its energy density is bigger than the Planck mass. It turns out that when you fit this model to the data, there's one free parameter here that you have to fit. Turns out that turns out to be about 10 to the 13 GeV. And then if you do that, it fits all the data. But then if you ask, at this displacement, phi greater than the Planck scale, but m given by 10 to the 13 GeV, if you look at what the energy density is, it's lower by a factor of 10 to the 12 than the Planck scale.
Is that not very fine-tuned to have an m so small? So, I mean,
Well, it's hard to say without knowing what the we don't really have any complete model of what the full quantum field theory of the universe is, or the full quantum gravity theory of the universe is. I mean, I'll say it this way: it's a lot less fine-tuned than the Higgs is. The Higgs is 11 orders of magnitude below this, and there's maybe it is fine. Maybe it is fine-tuned. I'm a little bit agnostic on that point. The bottom line is that it is the thing that I'm impressed by is that it's an observational fact that if you take the potential to have a mass of this value, that you're in the regime where quantum field theory and curved space-time should apply. You're at low enough energies, and when you apply that, you get from one free parameter, you get a lot more than one prediction correct. Yeah.
Why does the fine-tunedness of it depend on the actual value?
Depend on what?
So
there's sorry, you're right. Okay, yeah, both of your questions. Sorry, I'm thinking I was answering something different than I think you were asking. Now that you remind me, so there's two issues of fine tuning. One is like with the Higgs potential. Why is this mass parameter so much smaller than the cutoff scale, than the hypothetical cutoff scale of the theory? Like, as far as we know, the standard model is valid up to the Planck scale or the Gut scale or some very high cutoff, and when you calculate the quantum corrections to an m squared phi squared term, at least, yeah, even this, I'm not sure. I don't 100% buy the argument here, but the standard argument is that this guy receives quantum corrections that go as the cutoff squared, and so how did the first quantum correction cancel with the tree level part down to such a tiny fraction? What made them know about one another so that they could cancel out so precisely? And so you can ask that about the Higgs mass, which is 10 to the 2 GeV. You can also ask it about this guy, which is 10 to the 13 GeV. Without really knowing what the cutoff scale is of the theory, it's hard to know. It's hard to know how much. And also without knowing what relation ultimately conformal symmetry plays in relation to this guy, it's hard to know how seriously to take those arguments, I would say. Now, there's a separate question, which is that, we have taken, the m squared gives an intrinsic length scale. So let's say we fix m squared to be 10 to the 13 GeV. Then there's some intrinsic curvature scale of this potential, which gives some intrinsic ruler on field space. And so now it seems a bit funny now that, so that ruler is 10 to the 13 GeV, but we're going to initially displace the field by 10 to the 19 GeV. So our intrinsic curvature scale, I've not really drawn it correctly. I've drawn the picture so that the curvature scale looks comparable to the amount that I initially displaced it. But really the correct picture is that if the potential looks like this, so the ruler is this big, that I've displaced it by a million times bigger than that. And the question is, why is the potential still being? Why would we still approximate the potential by a perfect quadratic? You know, you might say, oh, a potential should look like a quadratic sufficiently near its minimum. That's just Taylor's theorem. That's just the Taylor expansion. But you know, why are we still approximating it by a quadratic? A million times further away, a distance away that seems, in some sense, naively, not a small displacement from the origin. So there's a separate question of fine-tuning there, and that is the one that most disturbs quantum gravity folks. They don't like the idea that it's hard to find fundamental quantum gravity vacua well, it's hard to find fundamental quantum gravity vacua and reduce them to sort of real low energy physics. Period. But in particular, it's apparently very hard to find low energy potentials where the scale over which they remain small compared to the bottom line is they reduce to the same thing, because the low energy approximations they always get have scalar fields where the curvature scale is m Planck here, not 10 to the 13 GeV, not 10 to the minus 6 of m Planck. And so, but that ultimately is coming back to the hierarchy problem when they take the low energy approximation of their theories, they're always getting masses here that are what you would expect by the same arguments that you make when you're proposing the hierarchy problem. So yeah, as I say, it's you know, well, there are some puzzling things about this, about the size of this, and about this displacement relative to this size. My perspective is that it's you know, yeah, you should take those puzzles seriously, but you should take them less seriously than predictive successes if you get enough. You know, yeah. Okay, so sorry, I'm at risk of losing track of time, and then there's no makeup lecture tomorrow. So then I'm going to be there's no bleeding over into the next lecture. So I'm going to be out of luck, and it's going to be impossible for you guys to do your homework. So that's the homogeneous story. The idea is that it's kind of nice that a single scalar field, and even such a simple one, looks like it can support ultimately the right behavior: acceleration first, and then deceleration. But then people became much more impressed by inflation when, in the early 80s, they realized that exactly the same model, if you just displace the field, suppose you did try to just displace the field perfectly homogeneously up its potential, as this model suggests. Well, quantum mechanics forbids you from making it perfectly homogeneous. It has to be in its vacuum state, which has some 0 point. Every Fourier mode has some 0 point fluctuations and fluctuates a little bit. And now what we want to calculate is that as you let the field roll down, according to this homogeneous picture, those 0 point fluctuations get amplified by the background stretching of the universe into a scale invariant spectrum of perturbations, which matches the primordial one we see. Okay, and then people got much more impressed by that when that prediction turned out to match the observations of the cosmic microwave background 2 decades later. Okay, so perturbations. You know, so far, you know, roughly speaking, we have these two equations, right? These are our exact classical equations. And then these two guys below are the two independent equations that are the homogeneous approximations to those guys. Maybe just to avoid confusion, I've been so we had been talking about another homogeneous equation here. Rho dot is equal to minus 3h rho plus p, the continuity equation. So it turns out that these two guys are equivalent in the case of a single scalar field. So we can think of these two guys as being the two independent homogeneous equations that the homogeneous limits of these equations. But now we want to consider the case where we don't assume that the field is homogeneous, but we take the homogeneous approximation as a first approximation, because it apparently was the case in our early universe that it was nearly it's an observational fact that our early universe was nearly homogeneous, but with small perturbations. So we're going to do linear perturbation theory. We take this guy and we write it as a part that doesn't depend on the spatial coordinate, plus a little perturbation that does depend on the spatial coordinate. And similarly, we write the metric. The full metric now, we say, is the 0th order FRW metric, which does not depend on the spatial coordinates, only depends on t, plus a small perturbation to the metric, which does depend on the spatial coordinates. Okay, so now let's imagine we plug that into the two sides of this equation, and expand to first order. So we plug phi naught plus delta phi into that first equation. Well, so what do we get? We get box of phi naught plus delta phi plus v prime of phi naught plus delta phi. Well, so let's Taylor expand this guy immediately. So let's call that v double prime of phi naught. Sorry. Let's rewrite this guy as plus v prime of phi naught plus v double prime of v double prime of phi naught times delta phi. Okay, so that's equal to this plus this is equal to 0. But by assumption, the homogeneous part solves the homogeneous equation of motion. We've perturbed around a background that is also a solution of these equations. So this part plus this part already equals 0. I mean, it's already a solution of this equation over here. So we're left with some linearized equation for phi. Linearized equation for delta phi. And similarly, when we perturb the Einstein equations, so g mu nu becomes, so schematically we plug in the metric. Given a metric, you can calculate the Einstein tensor. So now let's plug in that perturbed metric, g0 plus delta g, and calculate as an expansion in delta g. Well, there's a leading part that would be present even if the perturbation delta g was 0. That would only depend on this guy. So we'll call that guy g mu nu 0. And then there's a perturbation here. Then there's a part that's linear in the perturbation. So there's g mu nu 1. Okay, and then on the right hand side, we have the same thing. We have a 0th order part that only depends on the homogeneous scalar field, and a first order part like so. So now, and again, these guys cancel because the homogeneous part is a solution of the Einstein equations by itself. We're perturbing around a solution, and so we have this perturbed equation: g mu nu perturbed is equal to 8 pi g newton t mu nu perturbed, which we could expand this out, and it would depend on just the various components of linearly on the various components of delta g, and this guy would depend linearly on the various components of delta phi. Okay, and so those would be our linearized equations of motion, the things that we would solve to find the mode functions. So now it turns out Yeah, that's how you would get the linearized equations of motion. Now, let's instead, turns out to be convenient both classically and then when we quantize to think about that a different way. That if we work at the level of the action, so if we take our full exact action there, the Einstein-Hilbert action plus the single scalar field, and we plug into there the if we plug into there, for phi we plug in phi naught plus delta phi, and for g mu nu we plug in g mu nu naught plus delta g. We get the action splits. Okay, so it splits into, again, there's a part of the action which is just homogeneous in the fields. It only depends on the leading order thing. Only depends on these homogeneous parts. Now the first order thing, if we work to first order in perturbations, that thing is going to vanish because that's the point of a classical solution, is that when you linearly perturb around a classical solution, which is what our homogeneous part is, it's an exact classical solution. If you linearly perturb the action, according to the classical equations, the perturbation is 0 to first order. So the first order perturbation here is 0. But there is a second order perturbation. If we work to second order in these perturbations, we just Taylor expand that action to second order, we get an action that is quadratic in the perturbations. So it's quadratic in the delta phis and the delta g's. And that action, if you just take that action and vary it with respect to delta phi and delta g, you get the equations of motion for delta phi and delta g, which are exactly these linear equations I just described this way. You get this linear equation g1 plus equals 8 pi g t mu nu 1, and this guy, perturbed Klein-Gordon equation, exactly just by varying this second order part of the action. Okay? Yeah.
It seems to me that you are neglecting terms like, well, if you have that box operator, you must have terms like delta g acting on phi 0, right?
That's actually very true. You're absolutely right. You're absolutely right. I was just sketching. That's true. That's absolutely true. So let's say this is actually the full g mu nu, and then you're right. If you perturb this out in terms of homogeneous and inhomogeneous parts, you'll get the unperturbed box operator, and then another term, like you say, that
Phi 0, yeah.
where phi 0 goes. But anyway, and the reason, yeah, sorry, I was being too. I just wanted to sketch that the idea is you can take the linearized equation, you can take the exact equations of motion, linearize them around an exact background. We're not going to actually do the calculation that way, so I'm not going to worry about the fact that I'm being rough. But the basic idea is clear. The point is that I want to make that you can get those equations of motion are exactly equivalent to what you get if you quadratically expand the action, and then take the quadratic part as the action for the linearized equations. You just vary the action as usual with respect to those variables. You get the linearized equations. Okay, except there are a couple of subtleties. So this sounds straightforward in principle. In practice, it is a mess. So I'll just make two important remarks about why it is subtle and why it is a mess before I tell you what the answer is here. But we're not going to drive the answer because it's a mess. We're just going to take the quadratic action and work with it. So two points basically. One is that there's a lot of gauge freedom here. So these expressions delta phi and delta g are ultimately very ambiguous. There's a lot more gauge freedom than physically independent degrees of freedom there. So if the point is, suppose I take a solution where I have phi naught, which only depends on t, and a small perturbation, which is both space and time dependent. And I have g, which only depends on t, and a small perturbation, which is space and time dependent. And then I make, so in other words, I have a nearly FRW space, nearly Friedman-Robinson-Walker space. But then I make a coordinate transformation. I change coordinates from x to new coordinates x prime, which are just my old coordinates plus a plus a tiny little correction, plus some arbitrary but small coordinate transformation. Well, if this coordinate transformation is small, in my new coordinates, I'll have new perturbations here that, again, because this was just a small coordinate transformation, they'll again just look like small perturbations around exactly the same homogeneous background. But the perturbations will be different. Okay, so there's some ambiguity in what perturbations are present around an FRW background. This is so-called gauge freedom of general relativity, as manifested in cosmology, basically. So you have to be careful about fixing the gauge. So you're only talking about, you're only following physical degrees of freedom in your calculation. And then there are also, okay, so then there's also this business that the Einstein equations are split into some dynamical equations and some equations that are purely constraints. Basically, there's 4 Bianchi identities that translate into four of the 10 Einstein equations being purely sort of constraint equations. And okay, so at the end, so so the sum total of this is that it's a straightforward but rather messy calculation to actually do this expansion. If you'd like to see a nice way to do the expansion, people did it kind of a lot of different ways, most of them rather messy. But then there was this very nice paper in 2003 by Juan Maldacena. The calculation, I don't mean to say it's not prohibitively hard. You could do it in, you could just read his paper and do it in an hour. It's worth doing once in your life, but we're not going to do it here. So that paper is, I recommend looking at it if you're interested. It's like section 2 of that paper where he does this. Yeah, it's Astro pH. It's really his one Astro pH. That's what you should look at. It's Astro pH 0210603. So this is a calculation where he actually expands the action up to third order because he's going to try. The paper is sort of famous because he does a good job of calculating the non-Gaussianities in this model, which come from the non-quadratic terms. But as a warm-up in section 2, he calculates the quadratic part nicely. So you should look there. So a very convenient gauge, which is the one that he uses. So I said we had this gauge freedom we have to fix. Very convenient gauge is, so there's this. Did you guys in Ruth's course, I think the answer is no, meet the ADM decomposition of the metric? No. Has anyone ever seen that? So there's this clever way of writing down the metric. Due to these authors' ADM, David, who are right? M is Meissner. Anyway, D is DeWitt. A might be Arnowit. Anyway. Where the point of this decomposition is that, so what do we have here? So the metric has 10 independent degrees of freedom, right? The metric is a symmetric 4x4 matrix, so it has 10 independent components in it. So here we've split those 10 components up in a convenient way. So we've taken coordinates, and so we have a spatial surface parameterized by the coordinates x. So those are the surface at constant t parameterized by these coordinates x. And then we have the time direction. So the metric on the three-dimensional spatial surface is what we're calling gamma ij here. So that's a three-dimensional metric, so it's a 3x3 symmetric matrix. So it has 6 components. It's not very well drawn, but 3x3 symmetric matrix has 6 components. I know you're all with me on that one. And then the rest of these guys, the remaining 4 components we've written as the so-called lapse and the so-called shift. Okay, and these basically have to do with how we have the universe sliced up into constant time surfaces, and the lapse and shift basically tell you, okay, as you take a step forward dt in proper time, in coordinate time dt, how much actual proper time has elapsed if you go normal to the surface. And then the shift vector is basically telling you, well, the coordinates here, the lines of constant coordinate go one way, whereas I'm drawing this is a bad diagram. Okay, ignore this. So the lines of coordinates, let's say, go through however you choose your coordinates, but then there are sort of natural lines associated with each surface which go perpendicularly from that surface to the next one. And there's a question of, what is the shift as you go from one time surface to the next? That's this guy, Ni. Anyway, the reason, without getting into detail, the reason what Arnowit does, no, I think it's Arnowit, not DeWitt. Arnowit, Deser, and Meisner. Are you with me, David?
Yep.
Yes. Okay. So sorry. The reason for this split is that if you plug is that I said the Einstein equations, there's 10 equations, but 4 of them are really constraint equations. They're not dynamical equations. They don't involve time derivatives. So you can use those 4 equations to, these quantities, n and ni, if you split up the metric like this, they're exactly the quantities that when you write out the action, they appear, but their time derivatives don't appear in the action. So when you vary with respect to them, you exactly get the constraint equations, and then you can use those constraint equations to remove the n and the ni from the action.
Is the n squared just the inner product of the ni?
No.
Oh, okay.
They're independent.
Okay.
So the point is that this is just a nice splitting of the metric. Again, this is a result I'm just quoting because it's too complicated to show on the board. But the point is that these guys are not dynamical variables, and you've split them up so that they can exactly just be determined by the constraints, whereas this guy is, if you want, a physically independent dynamical degree of freedom. But we still have to use the gauge freedom to cut it down. We still have four degrees of gauge freedom, right? Because you have 4 coordinates, each of which you can add an arbitrary function to when you make a coordinate transformation. So of the 6 components of this guy, we can still impose 4 gauge conditions to get it down to the 2 independent degrees of freedom. Okay, so this is here. So really, I'm just saying something that you've probably already heard in a different way in your GR class, which is that the metric has 10 components, but if you solve the vacuum Einstein equations, there's only 2 independent degrees of freedom in the metric. There's in other words, if you look at a gravitational wave propagating in this direction, it only has 2 independent polarizations. It doesn't have 6 independent polarizations or something like that. Okay, and so the gauge that we will work in. Now, if we had pure gravity, with the Einstein equations are really saying that there's only that 10, the number of components of the metric, gets cut down to 2 physical degrees of freedom, the 2 polarizations of the gravitational wave. Now, we are actually not just considering vacuum gravity. We have the metric, and we've added one other scalar field, one other additional degree of freedom. So we're going to be cutting down from 11 to 3. We add 1 to both sides, in other words. Now, these 3 guys over here, we're going to split up into 2 parts. The quote-unquote scalar part, okay, which is going to be responsible for the so-called scalar perturbations. So these are that is cosmology lingo for the things which will ultimately manifest themselves as density perturbations, the fluctuations in the temperature of the cosmic microwave background, the fluctuations in the energy density from point to point, and then tensor perturbations, which is, again, cosmology lingo for what are secretly just gravitational waves. Okay, so these are density perturbations. These are gravitational waves. Those are the physical degrees of freedom in this model. Okay, I think we desperately need to stop for a joke for 1 minute. So even though time is drawing nigh, actually, can we do a riddle instead? I have kind of a riddle. So what? Actually, wait. What has 8 eyes, 2 mouths, and 3 noses? Give you guys a few seconds. Anybody? The answer is a monster. You wanted to get the exact numbers? Anyway, okay. Turned out to be a stupid joke. I fooled you. Okay. So we are going to fix the gauge so that there is only these. We're going to fix the gauge so we had d phi was one of our perturbation variables, and then we had dg mu nu. We've done this ADM decomposition so that really of dg mu nu, well, 4 of those perturbations were just we've shunted them into these Lagrange multipliers n and ni, and then we have, so really we're talking about the perturbed spatial metric here, gamma ij. So that guy, now we want to impose 4 gauge conditions on this guy to fix the gauge. And so we're going to work in the gauge where delta phi is 0, there is no perturbation to the scalar field. And then delta g, the perturbation in the spatial metric, we'll write that this way. Okay, so in other words, if this, 2 zeta, this is conventionally called zeta, and then e to the 2 hij over here. So zeta and hij are going to be my 2 perturbation variables. So if they were both equal to 0, if this was 0, then this factor would just become 1. If this was 0, this is the exponential of a matrix. So if this guy was 0, this would just become delta ij. So the 3 metric would just reduce to the FRW one. A squared times delta ij, that's just the 3 metric in flat FRW universe. So these are our perturbations, and if you expand it to linear order, this would be 1 plus 2 zeta, and this guy would be 1 plus 2 hij. Okay, and then so that's 1, and then we have to put a bunch of extra conditions on this guy, so it's not a general matrix. Remember, we want to get ourselves down to just 3 independent degrees of freedom. So the extra conditions we take on the matrix hij are that it is traceless, and that it is transverse. Okay, which means that if we look at any individual Fourier mode, if we Fourier decompose it and look at any of the individual Fourier modes, that Fourier wave vector contracted with the matrix is 0. Okay, so we split it up like this because this guy is, then this only has 2 independent degrees of freedom. Those are exactly the 2 degrees of freedom of the gravitational wave, whereas this guy is just 1 degree of freedom, zeta. It's just a single scalar function. And so again, these are the gravitational waves. These are the density perturbations. Okay, so there's an exactly parallel calculation for how inflation produces a spectrum of perturbations in zeta and produces a spectrum of perturbations in hij. Inflation predicts that there should be a scale invariant spectrum of both of these guys, but it doesn't predict their relative amplitude. This guy we've already measured. This guy is responsible, if inflation is right, for the observed fluctuations in the cosmic microwave background. This guy, we are hoping to measure. The Planck team is hard at work, and a bunch of other experiments are hard at work measuring the polarization of the cosmic microwave background and hoping to extract from it the first measurement of primordial gravitational waves produced by inflation, which could be detected as early as this year when Planck announces its results. But we're just going to focus on this guy, density perturbations. In the notes, and in the problem set, you just are going to calculate this guy. In the notes, I also, in parallel, go through this one. The calculation is very closely parallel if you're interested. Okay, so what did Maldacena show in this paper? He wasn't the first to show it, but he gave it, as I say, an elegant derivation of it, or as elegant as it gets. It was not, it's a bit of a mess still, but a pretty nice derivation of it. He showed that if you just plug these perturbations into our original action there, expand it to second order, like we said somewhere. Where did I say to expand it to second order? Lost it. Oh yeah, here. Expand it to second order and focus on the so there's a second order term in the action, and it turns out it breaks into two parts. There's one term that only depends quadratically on zeta, one term that depends quadratically on hij. They don't talk to each other. Let's just look at the part that depends quadratically on zeta. Okay, so that's the result I'm just going to quote and not derive, but you can look at that paper if you would like to derive it. It's not more than a couple of hours of your time, possibly even one. But anyway, so the action for zeta is every time I try to write zeta, I write some other Greek letter that I don't know the name of. It's a major bug. Okay, so what is going on with this? What is going on with this expression? So this is the action. This says minus 1/2 d eta, the conformal time, dx cubed. That's the co-moving spatial coordinate in flat FRW. Times z squared. This is not a perturbation. This is a background function of time. Okay, and it turns out to be that z squared of tau, z squared of eta, is just 2 epsilon, the slow roll parameter epsilon. So I calculate the epsilon over there the way it's defined, and then times a squared zeta. So in other words, if epsilon is constant, which it nearly is during inflation, to a first approximation, z squared is just proportional to a. It's basically just a slightly modified scale factor. Really, more correctly, it is the effective scale factor felt by this massless scalar field. Okay, so in other words, if I took z and I replaced it by a squared here, then this would be exactly the action for a free massless scalar field living on the Minkowski metric. In other words, this would be exactly the action g mu nu d mu z. It's really annoying. I do that. Okay, so in other words, if I just took this Lagrangian and expanded out and just plugged in the flat FRW metric here, but with scale, but I called the scale factor instead of a, I called it z, I would get exactly this expression. Okay, so this expression says this perturbation acts exactly like free scalar field living on flat FRW background. Okay, so now we just want to proceed to quantize it in the way that I described in the previous lecture, previous lectures, 2 lectures ago mainly. So we calculate pi by differentiating the Lagrangian with respect to zeta. Maybe we'll just switch and no longer call it zeta and just call it whatever this other letter is. So you'll go through this on the homework, but you differentiate the Lagrangian with respect to zeta to calculate pi. With respect to zeta prime, I should say, where prime here means, zeta prime means, anything prime means from now on d variable d eta. Okay, I can confidently say that that's what that notation will mean from now until the end of the course. Okay, now we impose the equal time commutation relations. You know, zeta with zeta is 0, and pi with pi is 0, and zeta with pi is I, with the delta function in the difference in their positions. And then we say, okay, but let's do what Dirac taught us to do, and instead expand those functions in terms of creation and annihilation operators. Okay, and now what we used to take our annihilation operator. Okay, here's what I mean. We used to take our annihilation operator and do an expansion like this. We said there's the annihilation operator times the. Okay, please just ignore that that's the wrong letter. A positive frequency solution of the equation of motion that follows from here, and a corresponding negative frequency solution. So now each of these positive and negative frequency solutions, in Friedman, Robertson, Walker space-time, we want to write those. We want to write those as follows. Okay. We will write. It'll factor. The solution will factor into, because this guy depends on space and time. We'll factor it into the part that depends on space, which is just going to go by translational invariance, by spatial translational invariance. That'll just be like this, e to the ik dot x. And then a part that depends on time. Okay, and for the part that depends on time, it's not going to depend on the direction of k by isotropy. It's only going to depend on the magnitude of k. So I'll drop the vector on top of k. Okay, so if we just rewrite that guy, if we just rewrite that expression like some operator times e to the I k dot x. We just pull out the e to the I k dot x. And there's some operator here. Comparing these two expressions, you'll find that this operator here is a sub k times the mode function that we called the purely time-dependent mode function zeta sub k, and then plus a of minus k vector times the complex conjugate of zeta sub k. Okay, and then turns out, so then we're just going to, again, take the a's and a daggers to obey the usual commutation relations, that all the a's commute with all the a's, all the a daggers commute with all the a daggers, all the a's, and the a daggers commute with except the ones that have the same value of k. They don't commute with one another. Now, as you'll check, this is kind of an inverse to the way we did it in the previous lecture. But if you check, in order for these commutation relations to be consistent with these commutation relations and this expansion, one of the things you'll check on the homework is that implies a normalization condition on those functions, which is that they will be normalized as, let me not screw it up. They will be normalized as, what they be? Where did this go? Does anyone see where it is in my notes? Oh yeah. So the normalization condition is that the Wronskian of the mode, so the Wronskian of a function is exactly this thing. Okay, the Wronskian of this function turns out to be has to be I over z squared. Okay. We're so close, I'm going to make it. I really am. I think I started at 10. I think I started at 20 till. I'm going to make it. It's incredible. I am proud of myself. I'm going to just talk about it until everyone else. Okay, so we said these guys. Okay, so now the thing we want to calculate. So what is our goal? Our goal is to calculate the so-called power spectrum of zeta. So what is that? The power spectrum of the primordial scalar perturbations. Well, what it means is it is the, if we take the expectation value of our operator zeta at any point in space, okay, if we calculate, so this, if we squared the operator zeta, that's of course supposed to say zeta, and we took its vacuum expectation value, where the vacuum here is defined to be the vacuum with respect to those creation and annihilation operators. It's annihilated by all of those annihilation operators. We take its expectation value. Well, this thing will formally diverge, but it receives contributions from different wavelengths. Okay, so it turns out that when we this is another thing you'll show on the homework. If you evaluate this expectation value, it formally is some integral d cubed k over some stuff. That stuff doesn't depend on the direction of k, so you can change this d cubed k into 4 pi k squared dk. Just changes the wave number. In other words, change from an integral change the integral from an integral over the wave vector to the integral over the wave number, just the magnitude of k. So when you do that, it's going to turn into the integral of dk over k, or in other words, d log k, times some stuff. Okay, that stuff is the power spectrum of zeta. Okay, so in other words, it is the contribution per interval of d log k to the variation to the variance of the scalar field to the variance of the scalar perturbation zeta in the early universe. Or in other words, the power spectrum of zeta as a function of k is d log k of this. If we just take d log k of this, it just strips off the integral in the d log k and leaves us with this. Okay, and so on the homework, you'll just be plugging this in and finding, what is this thing in here? And it's a simple calculation to show that that is k cubed over 2 pi squared times the magnitude of our mode of our time-dependent mode function. So in other words, this guy, the purely time-dependent mode function. Corresponding to the wave number k. Okay, and by the way, there's a confusion in the literature. Not a confusion. There's different people just use a different name for this variable. There's two common ones. Some people call it zeta. Some people call the same thing r. Anyways, it's in words it's called the co-moving curvature perturbation, and it's the standard thing that you see quoted in, for example, in the WMAP papers when they're talking about their constraints on the primordial power spectrum. So that's the thing we're trying to calculate. That's the thing they measure. That's the thing we're trying to calculate. And what we want to get, is that it is a function that over the range of wavelengths that are inside our horizon today, it's a function whose size is about 10 to the minus 10. And it's pretty much independent of wavelength. So it goes as a power law, and it's almost k to the 0. Turns out that more accurately, it's been measured to be k to the minus 0.04 plus or minus 0.01. So we want to calculate that it's an expression. We want to calculate an expression for it that can be compared to this. So, you know, well, we're almost there. We just need to know that if we just need to know what is the value of this guy. We want to evaluate this guy at the end of inflation. So inflation, we give some input value for this guy corresponding to a definition of the vacuum state, and then we let it evolve through inflation. And then at the end of inflation, we want to ask what is the square? What is the absolute value squared of this mode function by the time we get to the end of inflation? So for that, we need to know we need to basically solve its equation of motion to find what the actual mode functions look like so we can follow them from the beginning to the end of inflation. Okay, so if you take the action up there, that action for zeta, vary it with respect to zeta, and then go to Fourier space, you find that it looks like this. Okay, so in other words, it looks a lot like the homogeneous equation of motion for phi, especially if we take v prime to be m squared phi, like it would be for a massive scalar field. In other words, there's an acceleration term where we have zeta twice time differentiated. There is a friction term where we have some time-dependent coefficient times the velocity of zeta. And then there's a harmonic term. So in other words, if we didn't have this term, this would just be the equation for the simple harmonic oscillator. If we had this term, this would be the equation for a particle moving with respect to a time-dependent friction force. But we have them both. Okay, so in general, we can't solve this equation exactly, but we can solve it in two important regimes. So remember, the picture yesterday was as follows: that during inflation, there are two relevant sizes. Okay, this k is equal to 2 pi over the co-moving wavelength. This is the co-moving k, and corresponds to 2 pi over the co-moving wavelength of some perturbation. And initially, in the very early universe, it was very much smaller than the Hubble radius, 1 over h. But then when the universe accelerates during inflation, the Hubble radius is constant or grows slowly, but the wavelength grows much faster. And so the wavelength, soon this guy becomes a very long wavelength mode, much longer than the Hubble radius. Okay, and so what we want to do is, there's two regimes. When the wavelength is much smaller than the Hubble radius, that equation is easy to solve. And then when the equation is much longer than the Hubble radius, that equation is easy to solve. So let's just solve it in those two regimes, mash them together, and then once we've mashed them together, we'll get a nice expression for what the what the mode function is when it's way outside the horizon, which is where it is by the end of inflation. Okay, we're interested in modes that by the time inflation ends here, those modes have gotten way outside the horizon. Okay, so when the mode is very short relative to the Hubble horizon, that's the limit in which this term, the frictional force, is very weak with respect to the harmonic forcing, the spring constant. So in that regime, this is an underdamped oscillator, and you can get a good approximation of the solution by, if you define zeta sub k is equal to z v sub k, if you just plug that expansion in there, so you just pull out a factor of z from zeta to define a new variable v, the convenient thing is that if you just plug that into that equation, oops, did I do that wrong? Yeah, I did. This should be z to the minus 1. If you plug that into that equation, you find that the friction term just drops out. Okay, so now we just have the acceleration term and the forcing term, but now instead of just a constant spring constant, we have a time-dependent spring constant. But you'll convince yourself that in the regime where this guy is, in the regime where this is much shorter than this at the beginning of inflation, which is the regime where this trick is useful, this term is negligible relative to this term. So basically, V just obeys this simple equation of motion, and so we get e to the plus or minus ik eta is the solution of this equation. That's the solution for V. And then to get a solution for zeta, we just have to put back the factor of z. Okay, so 1 over z times that. Those are the two independent solutions for zeta at early times. Now then we just have to add a normalization constant to this to make sure that it satisfies this Wronskian normalization condition. And when we add that constant, it's another one of these things you'll check on the homework, but it just adds an extra factor of 1 over root 2k. Okay, so that's the solution inside the horizon. And let's focus on the positive frequency solution, because that's really what we meant by zeta sub k. We call the negative frequency solution here zeta sub k star. Right? We just want the positive frequency solution. So now, what about outside the horizon? Well, that's even easier. That's the case where the forcing term turns off. This is a particle. So if zeta double prime was just equal to 0, that would be a particle just gliding along. That's Newton's law for a particle that's gliding along subject to no force. And now we just turn on a big frictional force. It's obvious what happens. It just comes to a halt. The frictional force just stops it, and there's no other force acting on, because this guy is negligible. In other words, when we go outside the horizon, the thing that you'll convince yourself is that that's exactly the regime in which this term becomes negligible relative to this term. So there's no forcing, only friction. The field just grinds to a halt shortly after it goes outside the horizon. So it's doing this. So our job now is just this. We have the solution inside the horizon. It's constant up until, that's how the solution behaves until the mode gets to be long enough that it goes outside the horizon. Up until that point, it's given by this, and then at that point, friction just freezes it at whatever value it was at the moment it crossed the horizon. And that, to a first approximation, is its value forever after it goes outside the horizon. Okay, so our job really is just to calculate what is the value of this function at the moment of horizon crossing. Well, so horizon crossing is the moment when, remember, it's the moment where the Hubble radius, 1 over h, is equal to the wavelength of the mode. Well, permit me, in order to get the standard expression just right, permit me to say that it's the moment when 1 over the Hubble radius is equal to the wavelength of the mode divided by 2 pi. Okay, in other words, that if you just turn this guy over, that's this is where the physical Hubble radius is equal to the physical wavelength divided by 2 pi. The physical wavelength is a times the co-moving wavelength. So if you just pull that a down here, flip everything over, and call 2 pi over the co-moving wavelength k, that's the point when AH is equal to k. Okay, that's the horizon is a given mode of wavelength k. Remember, this is its constant co-moving wave. I said wavelength. It's constant co-moving wave number k. This is 2 pi over its co-moving wavelength. This side is constant. This side is changing in time. At the moment when this becomes equal to this, that's exactly the moment in cosmic history when this mode crosses outside the horizon. So what we can do here is use the fact that, as I mentioned before, z is, remember, z squared was defined to be 2 epsilon times a squared. So z is square root of 2 epsilon times a. And so at the moment of horizon crossing, let's call that moment star. this equation is true. So A is equal to the co-moving wavelength of the mode divided by h. And then this is just some exponential. This is just some phase. We're going to take the absolute value squared of this thing anyway. So that's just going to go to 1. So the only thing we really needed to evaluate was what this guy was. So in other words, let's take this expression squared. So 1 over 2k times 1 over z squared, where z at the moment of horizon crossing is given by this. That's the value of zeta outside the horizon that we should plug into this formula. And so if you do that, if you just plug into that formula, you get the famous Slow-Roll expression that P of zeta is equal to 1 over 2 epsilon times h over 2 pi m Planck squared. Okay? So the first thing to say is that because during inflation, A is growing exponentially while h is only changing slowly, if you look at h as a function of k, that's the reason why this is almost k to the 0. Okay? In other words, you scan across different wavelengths cross a huge range of different wavelengths cross the horizon very rapidly because they're growing exponentially in time, while h is just sitting there constant or just barely growing. So for all the different values of k at which we evaluate this, remember we're evaluating for each value of k here, for each wave number that we look at in the early universe, we're evaluating the value of the slow roll parameter epsilon and the value of the Hubble constant here at the moment that mode k crossed the horizon. But during inflation, tons of these modes are crossing the horizon. E to the 60 of these modes are crossing the horizon. A huge range of modes are crossing the horizon, while epsilon and h have barely had time to change at all. So as a result, the result is virtually independent of k. It's given, so it's essentially k to the 0, which is the observed fact. And if you calculate in more detail, which we won't do on the I mean, this is the ultimate goal of the problem on the problem set. But from here you can derive, in particular, what is the exact tilt here, which is commonly called ns minus 1, so-called, or ns is we call that the spectral index, and that's given exactly in terms of the potential. If you know v of phi, you can calculate what this guy is as the field rolls down the hill. Anyway, you can calculate everything. The only thing we calculate in the homework is this expression. The only really important thing I want to get across to you is the fact that yesterday I was saying that because the temperature of de Sitter space stays nearly constant, because the temperature of the oven stays nearly constant, that's the explanation of why you get a scale invariant spectrum of perturbations. This just concretely gives the exact, the idea is to derive the exact quantitative result that shows that is the case. You'll learn from the problem set basically what is the definition of this guy and why is it given by this formula that is nearly independent of k. Remember that this is exactly, h over 2 pi was exactly the expression we got for the de Sitter temperature. So the fact that the de Sitter temperature was nearly constant is exactly appearing here in the fact that h over 2 pi is nearly constant as the universe was accelerating at early times. Yeah, that's it. So I apologize. It had to go rather fast and be rather sketchy here, but again, the point is to do it in more detail on the homework. I did not get done as quickly as I thought I was going to. Anyway, that's it. Could I just, as a final thing, say thanks to David, who was super helpful throughout the course. Thanks for listening. yeah, if you have any other questions, feel free to come by and ask me about them.